Hello, welcome back to Computer Vision Zero to Hero blog series. Today we are going to talk more about cross entropy loss. So, in the last post, we trained a simple dense neural network and we just simply used cross entropy as our loss without much explanations. And this is fine. Machine learning engineers often do that because there are only a few simple losses. So for regression, we pretty much always use mean squared error, and then for classification, this is almost always cross entropy. But there is one quite simple explanation that I guess helps you understand it on a deeper level. So we are going to go through that today. And it starts with the probability theory, really. So imagine we have a situation like this. So we have a generator that generates balls with probability of P being black and then probability of 1 minus P being white. And let's say like it's a button, you press on it, and every time you press on it, out pops the ball. And so you pressed it 5 times and you got white, black, black. So what would be the probability of the first ball being white? It will just be 1 minus P. Similar to second ball being black, that will be P. And then of these two events, the sort of probability of the union is going to be multiplication of the two probabilities. And the probability of this entire sequence of white, black, black is going to be this thing. So it ends up being 1 minus P squared times P cubed. And this overall probability of the union is called the likelihood. Now we are going to try to solve the reverse problem. So let's say that we are in the real world, we see the actual 5 balls with their colors, and we try to guess what the generator was. So we try to give our best estimate for the probability P. We have no way of saying that exactly because there's always a chance that this particular picture can be generated with anything, basically. But we can have our best guess, and the best guess is something that leads to the maximum likelihood. So this is basically just the ideal P that maximizes the likelihood of getting this specific sequence. We can get P from this. For that, we just calculate the derivative from P. We end up with 3P squared times 1 minus P squared minus 2P cubed times 1 minus P. And we equate that to 0 to find the max. So first we move this little thing here to the right. Then we cross out P squared and 1 minus P. We end up with 3 times 1 minus P equals to 2P. And from that we quickly get P equals to 0.6 or 60%. Now, we could have gotten the same by just dividing the number of black balls by all balls. But still, this is like the general rule that you can use to find the generator behind some event that already happened with the specific outcomes for each throw, basically. Now, we want to use that as a loss function, as something that minimizing which can lead to better neural network for it to solve the problem that we want. Before that, though, we have a problem because likelihood is what we call not additive. So if we have 2 samples, the loss of sample 1 plus sample 2 is not going to be sum of 2 losses because the likelihood of union of these 2 events is going to be multiplication of likelihoods. But we can turn that into something that is additive by just putting the log in front of it, like this. And we also need a minus in front to make it a loss function. So we want to minimize it, not maximize it. And the minimum of this loss function corresponds exactly to the maximum of log likelihood because log is a continuous function. So wherever there is maximum for log likelihood is also going to be in the maximum for likelihood itself. So this is the loss, and log likelihood is exactly the same as cross entropy. Now, in neural networks, this is going to be similar. The picture is slightly different now. So now you have image on the input, you have some interconnected dense layers that output either one number for binary classification or several numbers, one per class, for multi-level classification. And we usually do it in such a way that the actual outputs of the network are not bounded, so they can be in arbitrary range. But then for binary classification, we apply sigmoid activation function, which is this S form that goes from 0 to 1. It basically turns arbitrary number into something that can be interpreted as probability, so a number from 0 to 1. And then for multi-label classification, the sort of generalization of sigmoid is softmax. This is the precise formula for softmax, but basically all it does is just turns a vector of probabilities into something, a vector of any numbers, in any range, into something that can be interpreted as probabilities. So every coordinate after softmax is from 0 to 1, and the sum adapts to 1 as well. And the overall picture will be the same. So now instead of like these 5 black and white balls, we'll have a batch of images, each with its own label, and then the network will output some prediction for each of the images. And we want to minimize this overall log loss on this specific batch, and then we do it batch by batch, right? And this is how it looked like in the previous Jupyter notebook. So before we actually trained the network, we printed out the actual predictions of the network, and we got something like this. And then the prediction was something close to 2.3, right? So how do we actually get there, right? So first of all, these predictions are just random, because we just randomly initialized the network, and they all are pretty close to 0. And now if we take softmax out of that, we get probabilities. And now these probabilities are all close to 10%, which basically corresponds to random guessing on one of 10 digits, right? Then to get the actual loss, we also need the label, which is 7 in this case. So we get the predicted probability for this specific label, right? Even if it is not the max here, right? We just need probability for class 7, which quite confusingly, not confusingly, corresponds to 7's index, which is 0.1080, right? And then we also need to compute minus log from that. And this is what we get, right? So we get exactly 2.2848. So for networks that we have just initialized, it will always be something about 2.3, simply because 2.3 is log of 10%, right? Important thing here is, even though the model predicted 10 different numbers, only one of them is going to be used to get to propagate the gradient backwards, right? So even though the network was pretty sure that it was 9, it was 8, we only propagate gradients from the label that we actually have for this sample. So the gradients are only going to flow backwards from this one output. And let's also look at the same thing after the training. So now the actual predictions are completely different. Some of them are negative and quite high, and then some of them are positive and quite high. Then if we go for softmax from this, we get a different picture. So now the network is pretty sure that that's a 7. We're still looking at the same example for the number 7. There it is. And the loss is pretty close to 1 now. So it's pretty close to 0. So this is how it works. Thank you, and see you again.